do proper dewatering of any construction site. Okay. Then we reviewed different methods of permeability, and I requested you to please go through from empirical formulas which are used to calculate permeability. I hope you have done it so far. So if not yet, please go through and share the formulas with each other so that we can see the list of the empirical formulas. And then we discussed about the laboratory permeability tests. We talked about some field tests like I didn't give you the details of these tests, but this is something I told you that they are used to get the permeability in a more accurate, but of course at the same time more costly way. So then the Darcy's law, some explanations into the laboratory permeability tests using constant head, falling head tests, and some details about the flexible versus rigid wall permeameters. You can see the details in the respective standards. Okay, these are some photographs or some details, brief details of permeameters, different types of permeameters. Then what are the issues in permeability testing? So especially regarding the high value of hydraulic gradients. Then like I said, to overcome these problems, you have to go for field pumping tests. And there are relationships available for calculating the permeability, in situ permeability of the ground. But like I said previously, that remember that this relationship is applicable only to this specific condition, which is called as unconfined aquifer. Okay, so if we have different types of aquifers like confined or mixed or some other situations, so in that case, different formulas are applicable. We talked about this approximation for single well formula and some specific terminologies used in field tests. Specifically, the most important terminologies are the free discharge surface and the influence range. Okay, this is how we calculate them, and this is how we get the value of the flow rate for multiple well systems, multi-wells, I would say. Okay, yeah, this is how we calculate the flow. Like I said previously, that it can be an open excavation, or it may be you can represent it as an equivalent well. Okay, so you can calculate the flow into the well with these formulations. Okay. Like we have Darcy's, we have single well formula, we have flow nets. Similarly, we have formulation for a pump well or a well point. Okay. So another point, whenever you are making deep excavations where groundwater tables are high, so remember that we have to make sure that the sand boiling or heaving of the excavated bottom of the excavation should not happen, and the condition should be fulfilled to avoid sand boiling and the other issues. Okay. Settlement to adjacent nearby structures. So of course, as you start lowering down the groundwater table, there will be change in effective stress, positive change, increase in stress. So increase in stress means increase in positive settlement. You can say the compression, which is actually referred as to consolidation settlement of the soil. And a very good example of this is the settlement of the Mexico City, which is like a very traditional example for consolidation settlements due to excessive dewatering. Okay. Then I think we just stopped at that point. Let's talk about now dewatering methods. Okay. What are different methods? There are methods which are for temporary dewatering, because sometimes you have to lower down the water table for just the construction period only, and then you can allow the water table to come back. So that's why we call that as a temporary dewatering. In some situations, you have to keep the water level below certain elevation. So in that case, you need some kind of permanent dewatering systems. So in temporary dewatering, we have 4 major categories: open pumping, free drainage, cut-offs, and exclusion. We will see all of them one by one. Similarly, we have some less commonly used dewatering techniques like horizontal well points, relief wells, artificial recharge, and groundwater remediation. So we'll see the details afterwards. Like I said, sometimes you need to lower down the groundwater table temporarily during the construction period, and sometimes you have to keep it permanently below a system. So permanent dewatering systems are far less commonly used. Of course, they are not that common. of course, as compared to the temporary or construction dewatering systems. And they are used for underground structures. For example, if you have basements below the groundwater table, and the basements have not been designed especially for as a watertight system, or you can say that they are not designed to take high uplift pressures of the groundwater tables. So in that case, you may have to keep the water table below certain level through permanent dewatering systems. You may, in case of retaining walls, you know that it's very important to keep the groundwater table below the foundation level. The reason is that once the soil which is being retained by the wall, if it gets saturated or if there is a groundwater table, so this becomes the unit weight of the soil will be more. Saturated unit weight is more, you know that, and it's going to put more earth pressures in the wall. Secondly, the water has its own pressure. This is going to be an additional pressure on the wall. So ultimately, the wall can fail due to high lateral pressures on the wall itself. So in retaining walls, it's very important to keep the water table always below the ground surface, below the foundation, below the level of the floor. Okay? Pavements, very critical structures. You know that you can't allow, even in any case, that the water level comes intact with any layer of the pavement, even may it be base or may it be sub base. So because you know that these materials are very sensitive to settlements, to cracking, and to spalling, and all these issues once there is a standing water in pavements. Earth slopes. The most important concern is once there is a high groundwater table, you know that the effective stress on the, the prospective shear plane or failure plane would be low because of the poor water pressures. So ultimately, if the effective stress is low, so you will have less shear strength available. So there are more chances of the slope failures, or you can call it as the landslide issues. Okay? So in that case, again, you have to keep the water levels below certain limits, certain levels in case of earth slopes. Embankment dams, we know that the phoretic line in embankment dams is something which controls the amount of seepage and the design of zoning and their location, type of zones. So all these things are dependent on where is the phoretic line itself. So that means controlling the water. Of course, we are using it in the category of permanent dewatering. That means that maintaining the phoretic level to certain position. So that's what is the objective of permanent dewatering. So that's why you can relate embankment dams in this topic. Okay? Temporary versus permanent. If you see, in case of temporary, of course, you have your excavations, temporary excavations, and below, of course, groundwater table, and then you have some temporary installments around the excavation or sometimes inside the excavation, so that you can pump out the water. And once your construction completes, so these systems are removed. But in case of permanent, for sure, there are permanent pumps, drainage systems which are installed, and they are working continuously. Okay? The main difference between temporary and permanent dewatering is that if you look at the details for temporary, the objective of temporary dewatering system is just to intercept the seepage, okay, and to improve the excavation and the backfill characteristics of the excavation to allow construction to proceed in a safe and efficient manner. So one thing is clear from here, that it's once you're doing the dewatering system, it also improves the characteristics of the soil itself, because the soil gets the water pressure gets reduced, and because of the reduction in water pressure, you get more effective stress, and then ultimately the soil gets improved. So it is kind of a ground improvement approach, but of course, the main objective is not the soil improvement. Main objective is dewatering of the soil itself for making the situation dry for your working area. In case of permanent dewatering, the main objective is not to intercept, to temporarily stop the seepage. The main objective is to make your systems waterproof. Okay, so that's the main objective. Or you can say that you want to reduce or eliminate the lateral and or uplift pressures. Like I said, in case of retaining walls, purpose of lowering the groundwater table is to reduce the lateral pressures. And in case of basements, if you have installed permanent dewatering systems, you want to reduce the uplift pressures on the basement wall, basement floors, the rafts, whatever have been designed for that basement. Okay. So this is the key difference between temporary and permanent dewatering systems. Uh, Along with these temporary and permanent, there is a third terminology which is sometimes ignored by the geotechnical engineers, maybe not given that importance, but it is very crucial because it's not just about keeping the temporary excavation dry from the water which is seeping as a groundwater table. Okay, it's about the surface water which can flow to your excavation as well. So just imagine in case of a heavy rainfall or some kind of flooding nearby. So if the water flows to, and you haven't designed the slopes, the drainage properly, and all the water flows to your excavation, so then even if you have installed the dewatering systems, so they are not going to be working that efficiently. So you have to make sure that the surface water is being controlled properly. So that's what is written over here, that the groundwater control alone cannot keep the excavation dry. The surface water has also to be controlled. So you need to make the slopes in a way that the water, surface water, in case of rainfall, it goes away from the excavation site. It doesn't go to the site itself. Okay. So sources of surface water, like I said, it could be rainfall, it could be nearby construction operations. There's some concreting going on, or some washing of the concreting plants is going on. So all that water uh, they may move to the construction site. Seepage through the cut-off walls. Maybe you have installed a temporary dewatering system around the excavation, but there is seepage going on through, so it can cause again your excavation to be in the wet conditions. Okay. Yeah, if you do not control the surface water properly, then you can have risk of localized flooding, like you can see in this figure. Okay, and of course, it can expose the soil in the excavation, and it can soften up because of the surface waters, and this can cause even the stability issues of the sides of the slopes, of the sides of the excavations. Okay. So it's a very serious, crucial part of excavations. So you have to be very careful that you have properly designed surface water control systems, especially in your deep excavations. Okay. Yeah. Now let's see what are actually the factors which you have to keep in mind before you select any type of dewatering system. So there's a list of that, and we'll be talking all about these factors one by one, which is subsurface conditions, what are the characteristics of the properties of the aquifer, size and depth of the excavation, especially how deep below the groundwater table you will be making your excavations. The method of excavation, that is also very important. What type of method of excavation you are using, and what type of the ground supports you're using. May it be like sheet piles, are you using secant piles, you are using soldier piles, or you are using some kind of cut-offs. So there are so many ways to have lateral ground support. So every method will control the method of dewatering system you want to install. Similarly, what is the type and how near they are to your proposed excavations. So that is also very important. So your system will be selected based on what is the type of the structure. When I say type, it means the importance of the structure, how important it is, the nearby structures, and how close it is to the excavation site. So these two parameters will again decide that what type of system you can use. Type of structure being built itself. So what is the type of structure you are building? How much watertight it needs to be? How much is the weight of the structure? Can it resist uplift forces once you remove the temporary system? So all these things, is it a lightweight structure or a heavy structure? So are you having basements or not? So all these things, they will also control the type of dewatering system you are selecting. The construction schedule, yeah, that's very important. Time is money. So what are the construction activities and how they are planned, so that will also be controlling the system you are selecting for dewatering. Yeah, a very important uh, factor, which is that if you have some kind of contaminants in the groundwater, especially there are some kind of industries, or maybe you can say there are some kind of uh, landfills nearby. So if you have some landfills or some kind of industry which is producing some contaminants, So if you do excessive dewatering, then these contaminants or the leachate from the landfills, they can move to the construction site, or you are actually causing them to move or mix into the groundwater. So that can also cause serious issues, environmental issues. So that's why it will again depend at what type of system you are using for dewatering in such situations. So these are some of the factors which will control which method of system, which method of dewatering will you use. Let's see all of them one by one in more details. Like subsurface conditions, it's very clear that if you have different types of soils or rocks, so of course your method of dewatering would be different because the permeability of all these materials will be totally different. Let's see this table where it gives you approximate range of K values, coefficient of permeability in centimeters per second. So you can see starting from gravel, it can go as high as 1 to 5 centimeters per second. And in case of the clays, if you look at here, homogeneous clays, it can go as low as 10 raised to minus 9 centimeter per second. And if you have shale, you know that shale is a highly over consolidated clay. So this gets permeability as low as 10 raised to minus 11. Sandstone, limestones, fractured rocks. So you can see different types of rocks and their relevant permeabilities. So it's very clear now that all these subsurface materials, they have different range of permeabilities. So your method to dewater the system will of course be depending on what type of soil you are in which you are doing your excavation. Okay. So this is just a chart given in the reference is given over here. So you can estimate roughly the horizontal, because normally with our routine permeability test, we get the permeability of the soil in vertical directions. So with this chart, you can get an idea about the coefficient of horizontal permeability of soils sometimes. Okay. So which is with the basis of knowing the D10 of the soil. Of course, it's an empirical relationship, so you may verify it through some kind of model or lab tests as well. Okay, because if you explore the literature, you will find a lot of methods, lab test methods to calculate the vertical as well as the horizontal permeability of the soil, which you call it as anisotropy with respect to permeability. So you can explore that. And yeah, one thing is clear from this figure, that this is based on field pumping test. That means quite reliable. Secondly, you can see quite a relationship, you can see that as the D50 is D10 of the soil, mean grain size of the soil is increasing, the horizontal permeability is also increasing at almost the same rate. Okay. Second condition or second factor which will control that what type of dewatering system you're using is the aquifer conditions, aquifer characteristics. I hope if you recall from your courses in undergrad where we talk about the groundwater and different types of terminologies used. So we may recall something, the words like aquifer. So you know, aquifer is a material, is a soil, is a rock which has the capability of transmit a large a volume of water. Okay, so any soil which can transmit large volume of water is called as aquifer. Now this aquifer can exist in a confined condition, it can exist in unconfined conditions. For example, if you see over here, so if you have sands and gravel like this situation, which is exposed to the atmospheric pressure, and if you install a piezometer inside, so it's going to be the water level will rise to the level of the water table itself. Okay, so which is called as atmospheric conditions. That's why you call it as unconfined aquifer. Whereas if you look at this sand or gravel layer, it's again aquifer, but the difference is this is now a confined, because you have a silt and you have kind of rock, a low permeable material at the bottom. So if you have low permeable material on top, low permeable material on bottom, so the aquifer will be called as a confined aquifer. And in that case, it's quite possible that an artesian condition will exist. When I say artesian, that means if you install a piezometer in this, so the level of water may rise the groundwater above the groundwater table, which is pressurized flow, because it becomes like a pipe flow. So pipe flow is always like a pressurized flow. So you may have high amount of head in this layer as compared to the unconfined aquifers. So now, if you look at this figure, we have different types of stratifications. It depends on what is the soil type on top. Do you have infiltration or not? what type of bedrock you have. Is it fresh rock, which is unweathered, or you have fractured rock? So all these things. So this will actually control that what type of method will you use, because every method is not applicable to all these situations. So you have to select the representative method for the conditions. So like I said, aquifer composition and distribution. What is the type, composition of the aquifer itself? Is it confined, unconfined? What type of material you have, and how is it distributed? Okay? Is it like in an unconfined situation? Is it in a confined situation? The conductivity, transmissivity, and storage coefficient of the aquifer. I would request you to please, you are familiar with the word hydraulic conductivity. Just go through the details of pumping tests and you will find these definitions over there. Read it, try to understand what is transmissibility and what is storage coefficient. Okay. Similarly, the flow rate calculation for the proposed construction area to be dewatered, that this is again that how much flow will get into the excavation, proposed excavation, and that will also, for a given aquifer, that will also control the type of method you are selecting for dewatering. So all these characteristics of the aquifer itself, they will decide the method to be used. Okay. Then there's an important concern, the location and environment. That's also very important. For example, if you look at these two situations, they are totally two different locations as well as environment. You see, it's a environment where you have temperatures like below zero or freezing temperatures. So in this case, your dewatering system will be different for sure. And your location is such that you don't have a nearby source which can recharge the system quickly. So, and if you look at this situation, you have different temperature systems. And the most important concern over here is if you are going for a deep excavation nearby this river, so you have a very a big source of quick recharge. So you are pumping out water from a certain excavation nearby to this source. So that source will be recharging the groundwater table very quickly. So maybe very, very high amount of flow rates towards the excavation can exist, and you have to have a very huge capacity of the dewatering systems. So this depends that what is the location and what is the environment where you're doing your deep excavations. Like I said, proximity of the existing structures, where are they existing? And like if you see in this situation, it's kind of a remote area, so you don't have any issues. You can dewater, you can remove water at any rate you want, and nothing is going to happen because you have nearby is nothing. So they're just fields. But in this case, your rate of pumping and your duration of pumping, the type of pumping method you are using, the groundwater removal method you are using, it's all going to affect the nearby structures. Okay, so in this case, the proximity is that you have structures nearby. In this case, you don't have anything. It's a remote situation. So in both cases, you cannot have the same dewatering systems and the dewatering methods as well. Okay, so you have to be careful. Construction schedule, like I said, that what is the design, what is the construction sequences you are following. Maybe sometimes they need to start construction in some part of the building, in some part of the excavation, some part is still under further excavations, or they need to keep it dry for a certain period of time. So what is your construction sequence? They may start building on some part, they may keep the other as still with no construction. So in these situations, the method you are using for dewatering will again be affected by what type of construction activities you have. So like you can see in this typical figure that within the basement there are dewatering systems installed. Maybe they're not clear, but you can see the pipes from here, and you can see the secant piles as well, the retaining system, and you can see nearby the existing structures. So this is a very sensitive dewatering system project. Okay. So like another important factor is the contaminations. So like I said before, that if you have a contaminated site nearby or an industry which is producing some kind of contaminants, and they are like they're not properly processing it, they're not treating it well, and they're just disposing it to the nearby streams or rivers. So in that case, of course, this is already causing damage to the environment, but Additional damage will be caused by your proposed dewatering system, because once you start dewatering, that means the groundwater will start flowing towards your excavation. You are causing an unbalance in the groundwater. So once the groundwater starts flowing to the pump well, so that means the contaminant will also start moving. So actually you are spreading the contaminants over a large area. So this is very important to take care that you have to see the proximity of your excavated sites, that you should not have any kind of landfills or contaminated sites which can cause the groundwater table to be contaminated further, and the contaminants can migrate towards the well. Okay? So this is what has to be carefully considered. Now let's talk about some detailed methods. Let's start with the temporary construction dewatering. Like the list of the temporary dewatering construction methods is open pumping, pre-drainage, cut-off, exclusions, and ground freezing. So these are 5 common methods used for temporary dewatering. Let's start with the open pumping. The word itself tells you the story. Open pumping, that you will make an open excavation. Okay, that means you allow the groundwater to enter into the excavation, and then you direct it into a low points called as sumps, and then you can install submersible pumps in these sumps, and you can pump out the water. So let me show you the figure first, and I'll come back to this explanation. Yeah, this is how it looks like. So you can see that you're making an excavation. So up to this level, you don't have an issue. So as soon as you reach at this level of excavation, the groundwater will be seeping into your excavated site. So you will make some kind of sump over here, as well as on the others on periphery of the excavation, I would say. And then the water will be collected in these sumps, and there are pumps installed which will pump out the water. So you are continuously pumping out the water, and at the same time you are proceeding with the excavation. So this is how it works. So this is the seepage coming from the slow phase. But the problem over here, you can see that you can uh, at a certain level, below a certain level, I'll talk about this from here. So you can see that this method is appropriate for soils with low to moderate K values. What's the reason of having low to moderate K? Because to make sure that the quantity of water discharged into excavation is controllable. You can clearly see from here that if it's like sand, gravels, or kind of very high K soils, then a lot of water will be moving into the excavation site. So maybe you need to install very large capacity pumps, or even it can cause instability of the side slopes of the excavation. So that's why this is applicable to low K soils. Okay. Generally, it's inexpensive because it doesn't involve any special dewatering system. It's just about pumping out the water using some submersible pumps, and it's effective as well, of course, for low K soils, low to moderate K soils. Disadvantage is that you will always see wet working conditions, because you can see water is always seeping from the slow face. So you have even water on the periphery of the excavation. So you can't do any construction activity, at least on the periphery, because there are sumps, open sumps, and the water is flowing into the sump. So the wet condition will always exist. Okay? That is kind of a disadvantage. So to overcome this problem, you can go for another method which is called as pre-drainage. So what does that mean? It means that rather than allowing the groundwater to come into the excavation, you intercept it before it reaches to the excavation. Like in this case, we are allowing it to come into the excavation. So you can stop it somewhere here so that it does not come into the excavation itself. Now, how to do that? So that is done uh, by a system I will show you afterwards. So you can say that the groundwater table is lowered before the excavation begins. So you can bring the water table down before you start your excavation. So it is suitable for wide range of soils, I would say for almost all soil types. And there are different further subsystems in pre-drainage. So you can do pre-drainage by pump well systems. You can do pre-drainage by well point systems, and you can do pre-drainage by ejector systems. Remember that all these three, they're almost similar in the main concept is pre-drainage, so they are similar from that perspective. The only difference is sometimes you are using vacuum to pump, and sometimes you are using the pump well system in a different perspective. And I'll show you all these three, the differences. So, but mostly they are using pumping well systems, okay, for pre-drainage purpose. Let's see all of them one by one. The first one is pump well system. Now you can see clearly that what we do in this case, just imagine that this is the proposed excavation. So it has not yet been done, and the water table is somewhere here, let's say. Okay, so of course your excavation required is below the groundwater table. So you have to bring the water table at least few feet or few meters below the lowest possible level of the excavation. So you have to bring it somewhere here, the phreatic surface. Okay. In this case, what normally we do is that you will install some wells, series of wells, like along the periphery of the excavation. And these wells are, like I said, they are installed before the excavation begins itself. So these wells are installed and then they are connected to a system of discharge network. You can see that. Okay, some pipelines which are collecting the water from all the wells around the periphery, and then you start removing the water, groundwater, and you can discharge it to a nearby source. So in this case, what's going to happen, and one thing to see is over here that you normally in pump well systems, you have the pumps are normally submersible pumps, which are kept in water and they are inside these wells. Okay, so you lower the water table to a certain level, and then the excavation is started. So that means this system will keep on working throughout the period of the construction until you reach to the ground surface, and then you start your superstructure construction, and then these systems may be removed. But they will be only removed depending on the factor that if this part of the structure, substructure, is heavy enough that it can take care of these uplift pressures. So if the uplift pressure is more than this part of this weight of the structure, then of course you have to wait for the superstructure construction until your uplift is much lower than the weight of the structure itself. So in that case, you can remove this watering system afterwards. Okay. This is suitable for groundwater table or confined aquifers and can lower the groundwater table 30 meters or more in a single lift without staging. That means you don't have to install the pumps in multiple stages. So even one single pump can work for this much depth, which is quite efficient system. This method can accommodate large flow rates, but of course it requires large investment in equipment because you need a lot of, you need to install a lot of pumps. You have to, of course, drill holes and then install pumps in these. And of course, these are not normal boreholes. These are pump wells. They have to be designed properly with the requirements of the filters and the plugs, and all these things. And then they have to be connected with the water collection systems. And then you need some control system. You need some settling tank where you can allow the sediments to settle, and then you can discharge the remaining clean water into some nearby source. So this system has to keep running for a certain period of time. So that makes it expensive. Yeah, this is one typical view of a system of series of wells installed along proposed excavation. You can see the excavation is going on, and this is installed all around the periphery. So this is the water collection main ring, and this is the pump itself. So there's a submersible pump inside this well. It is connected to this water collection ring, and then it is, of course, connected to the discharge network. Another one is called as well point system. It's similar to what we just discussed before. The only difference is that in this case, instead of having a system of wells, you can extract the water by applying vacuum to each well. But the point is, again, you have you have 1, 2, 3, and so on. So all these are series of wells, and then they are connected to a pipe called as a header pipe. Okay, and then this header pipe is basically connected to a system which will create vacuum for it. So you can pump out the water by vacuum, and then you can have a settling tank. You can remove the sediments, and then you can discharge it to the nearby site. So again, the point is that you are intercepting the groundwater before you start your excavation. So you lower down the groundwater to your proposed level, and then you start excavation. So the system has to keep on working until the excavation is done and the substructure has been constructed, and so on. So this is less expensive than pump wells, but because it is using vacuum, so vacuum has its own limitations. So that's why the depth is limited to 5 to 6 meter. But this does not mean that you cannot use below 5 to 6 meters this system. This means that every stage of pumping can be maximum can be of 5 to 6 meters. So you can install multiple stages. Okay, at different stages. So due to vacuum limitation, like I said, excavations that are deeper than 5 to 6 meters or more than that will require multiple stages of well points. So you will have a slope, and then you will have a bench over here. Okay, and on that bench you can install another well point system, and then you can have another bench, and then you can install another series of well point systems. So multiple well point systems can bring the water table down to as desired depth as you want. So this is kind of an image of the installed well point systems at a certain site. You can see that. Okay. So again, the system has to keep running throughout the completion of the construction of the substructures. Okay. The third category is, again, like I said, it is similar to the previous two cases in a way that you are pumping out the water before the excavation starts. So this is a special system called as eductor systems or ejector systems. This is used in soils where the permeability is very, very low. So you need actually some kind of special systems which can pump out water from a very low K soils. So this is well suited for deep excavations with stratified soils as well. Okay, and it is installed at relatively close spacing, similar to well point system, but it requires only a single stage to effect drawdowns up to 30 meters. So it's in other words, I can say it's kind of similar to well point systems like this one. Not well point, I should say pump well systems, but it's kind of a more, I would say, powerful system in terms of its depth of effective depth of up to 30 meters. Okay. Yeah, it's less expensive than pump wells, but it's inefficient when the required flow rates are high because it has its own limitations. So most commonly you would see this as a common method, pump well systems. It's a very common method. And second, and like the series I've, the sequence I've chosen is the way they are normally ranked in terms of their effectiveness. So pump well systems, they are given the top priority. Mostly they are used, then maybe well point systems, and then you can move to ejector or eductor systems. Okay, this is a typical schematic view of the ejector systems. So you can see you have installed the wells, multiple wells, and then you have some standby pumps. You have supply, that you have return, air vent, and return. So these kind of specific systems. You have concentric riser pipes over here. You can see that. Okay, and you can get the water dewatering from the system. Yeah, this figure shows you that if your excavation is sometimes complex or deep or some special circumstances, you can use even combination. It's not a rule that you will be using always deep wells or well points or open pumping alone. So you can make a combination. Like you can see over here that this is the original position of the groundwater table. So it was lowered down by a deep well system. You can see the deep well. Okay, and then there was a benching or step in the slope, and some well point system along the periphery have been installed, and this well point system further lowered the water table, and then you have the remaining amount of water goes into the open ditches or sumps, which can be removed by the pumping out the water, like in open pumping. Okay, so this is the combination of systems. So depending on the size, the location, the depth of the excavations, and all these things. Okay. Yeah, this is just a chart which can give you a typical well point spacing in granular soils. What spacing you will. So you can see that on this axis, this is the required depth of how much groundwater you want to lower down. Okay, let's say 10, for example. This is just an example. And your soil, pole over here means your reference soil. So your reference soil is gravel. So you will draw a line from 10 and you will move to the gravel. And then you can see the the spacing would be, for example, in gravel over here, it's about 1 feet. Okay, so you have to install very closely spaced pumps. If it's like 20, 30, and so on, so this is the axis where it is the lowering of the groundwater table. This is the reference soil. So you have to draw from this axis, you have to draw a line going to the respective soil type. Of course, you may think what is inside. So it depends on, for example, if it's over here gravel and then very fine gravel. So anything's in between, some intermediate sizes. So you can come up in between. You have coarse sand, you have medium sand, you have fine sand. So this is how you can draw the line, and you can get the spacing of the well points. Okay. In granular soils, similarly in spacing of the well points in stratified soils, this is how you can use these charts. Okay. Uh, but there's an example afterwards which I'll show you that you can make some empirical calculations to calculate the well spacings, and we'll do that in an example. Spacing of deep wells, it requires so you simply, what you can do is the spacing of deep wells required equals the perimeter of the excavation. So if you know the perimeter of the excavation, then the number of wells required, which you have calculated by depending on the flow or the amount of the dewatering or lowering of the groundwater table required. So if you already know the number of wells required, and if you have the perimeter of the excavation, so just dividing the perimeter with the number of wells will give you the spacing of the deep wells. That's another way you can do that. Okay, and we'll see it with the help of an example afterwards. Yeah, this is just a table giving you the approximate capacities of common pumps used in deep wells. So of course the capacity of the pump, it's depending on the inside, the inner diameter. ID over here stands for the inner diameter of the well. So for example, for 4-inch diameter, approximate maximum capacity in gallons per minute is about 90, and so on. So the size, inner size increases, the capacity of the pump will be increased. These are some charts, head versus the discharge for pumps. So if you know the total head in feet, if you know the inner diameter of the pump, you can get approximate discharge in gallons per minute from these charts. Okay. Yeah, let's see an example now to see how to use these methods and how to design a dewatering system. So if you look at the situation here, is we have an excavation, a planned excavation of 800 feet length and 500 feet width. So this is the plan view, and if you look at the elevational view, so this is the required depth of excavation is about 70 feet. Okay, and you can see the groundwater table is at 20 feet. So this means 50 feet at least minimum, I would say, is the lowering of the groundwater table. Along with that, if you see over here, that the requirement is that you have to lower down the groundwater table to 5 feet below the bottom of excavation. So 50 from here and 5 is this one. So you need a system, you need to design a system which will lower down the water table by 55 feet. Okay. So you can see that a soil which is in a situation, as you can see that we have glacial outwash sands and gravels of a relatively high K. The value of K is given. You may think that how did we get this number? Of course, for this you may have obtained the soil samples. You may have done some lab tests. Maybe you have used some empirical correlations, or maybe you have done some pumping tests or pressure tests in this aquifer, and you have got these numbers from there. So the very important thing is that before you are designing any dewatering system, you need to know the permeability of the soils underneath. And then you can see this soil is a very stiff lacustrine clay. I hope you can recall this word. Lacustrine means the lake deposits. Okay, so the K is quite low, and this, looking at this situation, you get an idea that this is representing a unconfined aquifer, because you have an aquifer over here which is exposed to atmospheric pressures, and then on the bottom you have a layer of very low K soil. So this is representing an unconfined aquifer situation. Okay. So let's see how to proceed with this problem. So I'll read the example statement again. So you have to design a deep well system. So the question is to design a deep well system to lower the groundwater table to 5 feet below the bottom of the excavation. So the very first thing you need to make calculations is the equivalent radius of the excavation, because you have seen the formula. All the formulas, they are considering an excavation as a well, as a pump well. So that means you have to convert this into an equivalent radius so that it can be considered as a one pump out of which you are pumping out the water. Of course, there will be series of wells, but it's going to be considered as one well, and then you will make the respective calculations. So to calculate the equivalent radius, you have its area, which is 800 into 500 divided by pi square root of that. So you can get 357 feet is the kind of an equivalent radius of this rectangular construction, rectangular excavation. Okay. Then height of the water level in the well, that is what you need in most of the formulations. You can see that once you will have like I'm saying, this is now is replaced by an imaginary well of 357 feet diameter, around which you have all the multiple wells. So height of water level in the well, you can see that it's going to be, so if you look at from here, so it is 160 feet total. Then you have 70 from here, so you get, like, this is going to be then 5 from here. So what does that mean? This means if you install a piezometer over here, okay, so if you install a piezometer over here, the level of the water would rise to 85 feet. Of course, if you do not do the pumping, the level of the water would rise to this level. Okay, but you have to keep it. You have to pump it, and you have to keep the level of the water in the well to 85 feet. I hope you understand this discussion. So I'm just calculating the height of water inside the well where you want to maintain the water during your excavation. So that is going to be from this is the reference, installing a piezometer, and then it's going to be 85 feet. Okay. If you want to see this H naught in more details, you can see previous slides. I've shown this parameter over there. Then influence range, very important number you need to calculate that once you are doing pumping, then up to what distance, radial distance, the water table will be drawn down. If you remember yesterday's discussion, I told you that drawdown at the well itself is maximum, and as you start moving away from the pumping well, the drawdown starts decreasing, and you have to look for a distance where the drawdown becomes 0, and that is called as influence range. And this is the formula which was discussed in previous slides. So you see is a constant, which is 3000 over here. H minus H is, you can see that over here. H is the initial height of the water table or the water level with reference to this datum. So it is 140 minus HW, or height of water in the well, or you can say that H naught, the same thing. So this is going to be 140 minus 85 into 0.3. This is actually converting this fit into meters per second, because this formula requires everything in meters. Okay, so this is 4.7 10 to minus 5. This is minus 5. You see over here, this was minus 3. So this divided by 100 will make it meters per second. So this will become minus 5. So this is to convert feet into meter. This is centimeter into meters. This is a constant, so you get the answer as 340 meters. So I mean to say that from the center of an imaginary well, pumping well over here, of a diameter of 357 feet, a radius of 357 feet, the range of influence will be about 340 meters. Means up to this range in all the directions, the water table will be affected. And this is very important for you to know, because if there are some important structures within this range, like from the center to 340 meters in all the directions, so that means you are causing a change in effective stress in all these directions. So change in effective stress means consolidation settlement. So you have to be very careful. If it's not a remote area, if there are nearby existing buildings, so you have to see how much the settlement can be caused due to this effect. Okay, so you got some important numbers from here. Equivalent radius, you got the height of water in the well, and you got the influence range. Now we can proceed with some of the calculations to calculate the flow into this excavation. Because once you know how much flow will be coming to the excavation, then you can design respectively the deep well systems or any type of well systems. So that's what I said, that you have to calculate rate of flow in the well. Again, remember that you may be thinking, where are the wells? We are representing this excavation as a equivalent radius of a well. Okay, so let's use the Darcy's law, or we can use all the possible methods we have and see what is the difference. So using Darcy's law, this is the formulation I've just shown you before. So you can see all the numbers we have already calculated, or they are known. The initial height of the water table, water level in the well, the influence range, the diameter, equivalent diameter or equivalent radius of the well, K is the permeability. So you may see a strange number over here, but this is actually we are looking for an answer in feet cube per minute, because it's easy to convert cubic feet per minute into gallons per minute. So that's why they are using this as in feet per minute. So actually this number, 4.7 into 10 to the minus 3 centimeters per second divided by 100 will make it meters per second, and then multiplying this with 3.281 will make it in feet per second, and then you can further divide it by 60, you will make it in feet per minute. Okay, so you will get this number like 0.00925 over here. Rest is just given numbers. Okay, so you get the value is roughly 2,600 gallons per minute. This is the flow which will be coming to the excavation. Okay, that means you have to design the pumping system accordingly. So you need to install pumps of this much capacity. Similarly, you can use other formulas to see what difference values you get, and you may choose the highest one to be on the safer side. So if you use a single well formula, the answer you get, you can see all the variables in the equation. So the answer you get, I'm sorry, this is, you can, yeah, is log values, you can use it minus or divided by the same thing. So you will get the answer as about 2,350 gallons per minute. And similarly, you can use flow rate into the wells using flow net. Yeah, of course, in this case, either flow net should be given to you, or you should be able to draw the flow net. And you can see a flow net has been drawn, an approximate flow net, and you can do that very easily. You can see that if you know this is the center of the well, of course, imaginary well on the center of the excavation, whose radius you already know is 375, I guess. Yeah, 357. Yeah, 357 feet. Okay, so half of it is 178.5. So what we have done over here, you know that it's a symmetrical situation. So they have drawn a flow net only for half part of it. So you don't need to draw the flow net on both sides. So flow net has been drawn on one side. So it's just like, because the situation is symmetrical all around. And the zone of influence, radius of influence, is we have already calculated, is it's one, although it's 1,130 feet, but for your calculations, where you want to draw the flow net, you can extend it to a larger range. Like in this case, they have extended it to 1,500 feet. Okay, so, and what is a flow net? You know that flow net is a combination of equipotential lines and the flow line. So you can see this is the first flow line, and maybe you will be thinking how to draw this line. So you have to have a zero drawdown over here, and you need a 5-foot drawdown over here. So because in the given example, it is required to have the water table at least 5 feet below the level of excavation. So this is 5 feet and this is 0. So you can draw a line like this, and this will give you the first equipotential line. And then you have the second equipotential line, third one, I'm sorry, the flow lines. The first flow line, second flow line, third flow line, and then the fourth one is along the base of this lacustrine deposit, this one. So this is the last flow line along the surface. Okay, so once you got these flow lines, you can draw equipotential lines. In this case, they're going to be very simple, because the rule says that the equipotential line should intersect with the flow lines perpendicularly. So that means all the lines would be very pretty straightforward lines like this. Okay. So you got number of flow lines, you got number of equipotential lines, and then flow lines minus 1 will give you the number of flow tubes or flow channels, which in this case is 1, 2, and 3, as you can see. And the number of equipotential lines, which you can see in this case, are 43. So the number of equipotential drops would be 42. So this is what you can use, I guess. Okay. Yeah, you may be thinking again that why this is 30 over here, because this figure has been drawn for a zone of influence for 1500 feet. So you can draw it to a zone. You can make your calculations up to 1130 feet according to scale. Somewhere here, maybe that finishes somewhere here. That's why number of lines being used, number of equipotential lines being used are 30 or 31, and this gives you an answer of 30. So flow tubes are 1, 2, and 3. Okay. So this is how this formula will work. Rest is just like numbers: K, H, H naught, R naught, NF. NF is, like I said, number of flow tubes: 1, 2, 3. And D is the number of equipotential drops starting from the center and going up to the zone of influence. According to this scale, it should end somewhere here. Okay, so you get 30 or 31, and you get the flow as flow coming into the well as about 1,782 gallons per minute. Okay. So you got 3 different numbers from 3 different methods. Then for the same example, what is mentioned or given that a pump test was done, and it indicated that the field permeability is not actually 4.7 into 10 to the minus 3. So this gives you an idea that this value has been established by a empirical formulation. So, but later on, they did a field test, and they had some data from the field test itself, and they found that the zone of influence is also more. It's about 2,200 feet, which is more than even 1,500, and the K value is also a bit higher than what was calculated based on empirical calculations. So now if you have different K, different R, you can just repeat all the solution again, and you can get the Q, the flow rate in gallons per minute using Darcy's law, using well formula, using flow net. So you can just get different values again. So I would request you to please solve these 3 equations again for these 2 new numbers of K as well as the zone of influence R. Okay. So you get these numbers. This is like I was talking about pumping well test for in situ pumpability. You know that you have to install a pump well, then you have some observation wells on both sides, then you have to record values like the level of water in both observation wells, the distance of each observation well, and knowing the Q, the pumping rate through the well. So all these numbers, if you have it with you, so you can use a formula to calculate the K of an aquifer. Again, this aquifer is a confined aquifer. So the formula we have seen before was for confined aquifer. For unconfined, the formula would be different. So once you got these numbers with you, now let's decide the layout of the deep wells. So if you look at this figure, we can see that it's just a calculation. You can it's an estimation. You can do it by any number to start with. For example, if we see over here what is being proposed, that the one deep well is suggested at this middle of this side, the shorter dimension. Then you have one at the corner, one at each corner. You can see that, okay, and one in the middle. So a simple rule used as one in the corner and one in the middle. So total, if you see overall number of deep wells which are proposed are 8. So you have 8 wells proposed. So they will be connected by a header pipe, means a pipe which will be collecting the flow which is coming out of these pumping wells, and then it needs a discharge pipe. So one thing is very clear from this figure, that if you decide the size, the diameter of this header pipe suitable for these 5 deep wells, then the same size will for sure will be good for this side, because on this side you have only 3 pumping wells, okay, deep wells. Over here you have 5. So if you decide a size for this, use the same on the other side, and then you need a discharge pipe. Now, of course, in case of discharge pump, the size of the pipe over here should be good enough to take care of the flow from all these 8 wells. So if you see, yeah, this is another formula which we did not use it before. You can use it. You can also calculate Q based on the multiple well systems. We had 4 methods, like if I recall. So we just use 3 over here. You can use the 4th one as well, okay, in which again everything is known, given. So you can get the flow from here is about 290 gallons per minute. Or let's use this as a basic number for calculations. or you can use take an average of all these or anything like that. Okay. So once you got Q, and remember this is the total flow coming into the excavation. So then if you divide it by 8, so this is the capacity of the pump, the well you require for each deep well. So 290 divided by 8 deep wells. So each pump in the deep well should have a capacity of at least 36.3 gallons per minute. Uh, Now if we talk about a size selection, so let's start with the minimum one, the 4-inch diameter. So for 36.6 gallons, because if you look at that table, I'll take you back. Yeah, you can see that the 4-inch well is sufficient to have a capacity of 90 gallons per minute. In our case, the capacity is 36. So the minimum diameter, inner diameter of well available is 4 inches. So you will use that, which is sufficient for 90 gallons per minute, actually. Okay. So you will have a pump of 4-inch diameter. You can see that. So that means you need the size of the header pipe now. So like I said, that if the header pipe size is sufficient for these 5 deep wells, it will be equally good for the other side as well. So 4-inch diameter for the size of the pipe should be sufficient to take, because you are getting about 40 or 36.6 gallons per minute from each well. So 36.6 into 5, so which gives you 181 gallons per minute. So if you have a pipe which can accommodate this much flow of 181 on this side as well as on this side, is going to be working fine, because you're getting 36 or about 40, 37 gallons per minute from each well. So that's the size of the header pipe you can get accordingly. And the capacity of the discharge pump required should be, of course, because you are getting 181 from this side and plus 36.6 into 3. So you have 3 pumps on this, 3 wells on this side as well. So 181 plus 36.6 into 3 will give you the overall capacity which you require for the discharge pump. So this is how you design a system. Another example before we stop for today's lecture is that you have an excavation of a power plant. You can see this one, proposed excavation is to be made near a river, so you have a flowing river nearby. A well array around the excavation is to be used to pre-drain the excavation site. You can see that's a pre-drainage concept. So on the periphery, you will be installing the well system. It should be pumping out the water and maintaining it below the required depth, which is actually the groundwater table must be drawn down to from 90 to 75. So if you look at this figure, so this is the elevational view. This is the excavation required is 20 feet. Okay, and then you require it for you need to draw it down from 90 feet to 75 feet. So from 90 to 75. Okay, so we were talking about this example. So like I was saying that the groundwater table must be drawn down from 90 feet. So from the top of the aquiclude, the initial level of water is 90. So you want to bring it down to 75. That means groundwater table lowering of 15 feet is required. So compute the total flow that will be required to draw the aquifer down to the required level. Of course, if you can make the calculations for flow, then the rest of the design of the pumps, their capacities is quite simple, because you just have to decide the diameter of the pumps and the size of the header pipes and the discharge systems that can be designed accordingly. So the main calculation is always to get the flow that will come to your excavation, okay, that will reach your excavation. In this case, a special scenario exists that you don't have to make calculations for influence zone specifically. It's a special problem, because you see over here, why do we need influence zone? That we want to see that once you are dewatering from an excavation, then what will be the range where the maximum drawdown or minimum drawdown will happen, or zero drawdown, I mean to say. In this case, you will not get a situation of zero drawdown. The reason is there is a river source nearby at just a distance of 750 feet from the center of the excavation. That means there is a continuous recharge to the groundwater table. So this continuous recharge will create a lot of flow, groundwater flow into your excavations. So there is a rule for such situations that you can use the zone of influence as twice of the distance from the excavation to a nearby recharge source. This is a recharge source, so just twice of that. This will give you the zone of influence, okay, which you can use it for your calculations. So let's see how to proceed with this example. Okay. So again, you can model it because the formulations we have are for an equivalent circular systems. So you can convert that into an equivalent radius, well radius method. So like I said, there is a recharging system nearby. So the zone of influence would be twice as that of the distance from the center to the recharge body. So 2 times 750 gives you 1500 feet. Equivalent well radius, like we have been doing before. So we have, if I go back, yeah, it's 300 by 300 feet of system of excavations. Yeah, so 300 feet by 300 feet of this periphery of the rings. So 300 feet by 300 feet divided by pi into square root of that will give you equivalent radius 169 feet. And using the same formula like we have been doing before, circular arrangements of wells, so you can get the total flow. Of course, again, remember that this is flow through unconfined aquifer. So you have the value of K is with you given. You have the initial level of the water 90, the level you want to bring it is 75, and then you have R is 1500, and the equivalent well radius is 169. So you can get the total flow rate is about 7.12 feet cube per second or 3200 gallons per minute. So, and you can, because you are looking for the capacity of the pump, so you can see that we have, if we see the figure itself, how many pumps we have, proposed pumps. So you have 4 and you have 12 pumps. So you can get the capacity of one pump, or each pump would be 3200 by 12, which is 270 gallons per minute for each pump. And of course, using that table we have just seen before, you can see the diameter of the pump itself, the size of the pump. If you see it in that table, let's see that. It's going to be roughly, yeah, you can see it over here. So a 6-inch diameter pump would be sufficient, because it's going to be okay for the flow rate we have for each pump, which is about, if you see in this example, is 270 gallons per minute for each pump. And then you can decide the size of the header pipe and the discharge system and everything accordingly. So yeah, I will just stop here for today's lecture, and then we will continue with this cutoff methods or seepage barriers, and then I'll be talking about permanent dewatering systems, and that will be the part 3 of this topic. So the part 2 concludes at this example. Thank you very much. Assalamu alaikum wa rahmatullahi wa barakatuh.